Okay, let's get started. So as promised, this week we're going to do two-port feedback representations. So since they're slightly different for every type of feedback, we're just going to go. And today covers shunt. So let's say we're going to do two-port. And then in particular, we're going to be looking at effects of loading. If you go back in your lectures, the first time we talked about feedback topologies, we sort of already did these two-port models. It's just that the feedback in those was always ideal. If it was shunt at the output, it wasn't really loading the amplifier, and then the feedback would be just the current source, things like that. So we're going to sort of start from there and then add the loading effects and see how that modifies the expressions for A and F, and then do some examples. So the first one we're going to do is shunt. And if you recall, we had something like this where we had the source. We're going to do, I'll write things mostly as admittances because everything is sort of in parallel, so it's going to be easier in the end. But essentially what this really looks like, you could also write it as a V source and R and Z source, so to speak, right? Which is kind of what we did earlier. So what we used to have was this goes into some amplifier with input impedance, and in this case I'll just call this Y11A, and then that develops some voltage VI at the input, and then the amplifier I can again either write it as a voltage-controlled voltage source with impedance, or I'll just write it in the Norton equivalent as Y21A times VI. And then I'll just write Y22A as the Norton parallel impedance. And that will go and load some Y load. Okay, and that was our amplifier. In a sense, we could say that, okay, this piece over here was our basic amplifier. And then we have the feedback. Because it's shunt, we have to take the output. So this is going to be VO. Take the output, feed it back. And then here, ideally, in the feedback circuit, we would just measure this voltage, right? So we would present infinite impedance or zero admittance into the feedback network. But, and so I'll keep it like this for now. And then on the other side, what we have is we try to add current. So this feedback has to produce, we'll call this Y12 feedback of V0. So this is V0. And then this would be the feedback circuit. So this current here would be I feedback, essentially. So this is sort of the view we had a few lectures ago when we started classifying the types of feedback. So we have shunt at the output because we're measuring voltage, and then we have shunt at the input, which means that the feedback network is in parallel with the amplifier at the input, so we can do current summation or subtraction. Right. Now, when we consider the impact of realistic feedback circuits, which is kind of the ones you build in the lab, the situation won't be as ideal. And you'll need to figure out how these additional circuit elements that get added as sort of non-idealities will affect how this picture looks like, right? So the first thing that's going to happen is that we're going to have some finite admittances here in the feedback network, and we'll just label them here as Y11F, which is kind of the input admittance into the feedback network. And then, again, on this side, we'll have Y22F. And then we're going to have a possible effect that the input actually gets to the output without going through the amplifier. We talked already about that in terms of the return ratio analysis and these topologies where you have this feed-forward path from the input through the feedback network without really going through the amplifier. And we have to represent that as another source here that will have Y21 F times VI. And then, to be really general, what amplifier itself could also have kind of a bilateral direction or the reverse direction of signal flow, although we can in many cases just neglect that, but just for completeness, we can also add that. So this would be Y12A times V out. Okay, so now that we've kind of added these things, we have sort of a complete picture of both bilateral signal flow through the amplifier as well as the feedback, as well as the loading that the feedback, in terms of impedances or admittances, that the feedback will impose on the main amplifier path. Right? And now, if you feel kind of like you want to do some math exercises, you can go write out the nodal expressions for this and just go ahead and solve it, right? And you'll see that even for very simple topologies, it kind of gets very involved, right? So what we do instead, even here we try to do some inspection analysis, right? And one of the things just to note is that the reason why we're doing these, let's say, Y-parameter representations, just for review for people who may have forgotten, both amplifier and the feedback network can be represented through this Y-parameter analysis, where, let's say, I have port 1 and port 2, and then V1I1, and then here V2I2. And then I can, in general, write this as I1 equals Y11 times V1 plus Y12 times V2. And then I2 will be Y21 times V1 plus Y22 times V2. And what this also means is that if I now start playing tricks with this circuit, I can actually extract what the parameters Y1 through Y22 are. For example, I can say that Y11 is I1 over V1 when V2 equals 0. So if I short the port 2, and then I measure current into the port 1 when I'm applying some test voltage at port 1, I'll be able to extract Y11. Okay? Then I can do the same thing with Y12 will be, again, I1 over V2 when V1 equals 0. So if I short port 1, I apply voltage at port 2, and I measure the current in port 1, I'll be able to get Y12. And correspondingly with Y21 would be I2 over V1 when V2 equals 0. And then finally, Y22 will be I2 over V2 when V1 equals 0. Okay. So these are exactly, if this sort of reminds you on what we did in return ratio, when we nulled the input, looked at the output, etc. So these are similar techniques. You essentially null the voltages. In this case, because this is shunt, we're really playing with voltages as the representation. The most convenient representation is this Y parameter, because everything is in parallel. And then we can start extracting different components here. So the name of the game will be to identify this feedback network. And then, as long as we can isolate the feedback network in terms of 2-port, we can then create this set of Y parameters that represent the feedback network by essentially nulling the inputs and outputs and measuring currents. And we construct the Y parameter representation. We can then map it back to this model. And we're going to go only once and solve kind of the expressions in this model so you can see what form it takes. And then you'll never again have to go through the whole thing. You just essentially plug in the expressions that you find from the feedback network. Right? So that's kind of the idea. So if we look at this network, what I can write is that IS, which is the input current, that's now my input current port, is YS plus Y11A plus Y11F times VI. Now notice that this here means that essentially YS, Y1A, and Y1F are all in parallel with each other, so admittances sum together. And voltage VI is the voltage that applies to these admittances, right? So that's kind of the current. So that determines the current that flows through all these admittances. And now the other part that we need is essentially the current from these controlled sources, this one and this one over here. And so we're going to write that as Y12A plus Y12 from the feedback, and then times V out, right? So that's the reverse signal flow that impacts the input current from the output voltage, both through the amplifier and through the feedback. Okay. The second expression that we have is that is what happens at the output network. And then we have Y21A plus Y21F times VI. These are the controlled sources in the forward direction, both through the feedback network and through the amplifier. And that current has to be equal to the current in the output admittances multiplied by the output voltage. Right, so here we have Y load plus Y22A plus Y22 for the feedback times V out. Now, just to make things a little bit simpler and not drag things, we're going to call this Y input, or the total input admittance. And then we're going to call this piece Y out, or the total output admittance. These are like real resistive values, right? And the rest are just the current controlled or voltage controlled current source coefficients. And so from the bottom equation, we can figure out what VO over VI is. So that will be minus Y21A plus Y21F over Y0, right? And then we can plug that into the top one. So I'll just write out the expression for VO over IS. And that will be Y21A plus Y21F. And then no longer YIYO minus Y21A plus Y21F times Y12A plus Y12F. Now we want to massage it a little bit to, this is essentially what we used to call closed loop gain, right? We're dividing the output voltage by the input signal value, which is IS. But we want to put it in some form that's very familiar to us. It should be a form of like A over 1 plus AF or something like that, right? And so if we take out the YI0, we can get something that looks like this, minus Y21A plus Y21F over YI0 over 1 plus, and then we have minus Y21A plus Y21F over YI0, and then times Y12A plus Y12F. Is that visible? Hardly? No? Okay. So this is Y12A and Y12F. Let me try to maybe. Let's do it. Yeah, the screen for some reason is smaller. So this will be the same expression as above, minus Y21A plus Y21F over YI0, and then times this piece over here, which is Y12A plus Y12F. Okay, so from here, you clearly see kind of the form. This is A. This is A as well. And then this piece is F. Right? So I have my A over 1 plus AF expression. So ACL is A over 1 plus A times F. So from here, I can kind of clearly say, OK, my A is, by definition, in this, or how we derived it, how we set up this network, is Y21A plus Y21F. So that's the controlled signal flow, all the gains in the forward direction. And then divided by YI/YO. And then F is going to be the gains in the feedback direction, Y12A plus Y12F. Usually, these Y parameters for the amplifier, I can find them very easily. I just map the amplifier in the, for example, if the amplifier was the transistor, GM would be Y21A, right? And then I just need to find out what those parameters are for the feedback network to be able to plug in here, and from here essentially get my A expression for F, closed loop gain, even the impedance formulas, right? And then I'm done. So if we take a look at these expressions, there are usually some things that how people who use two-port analysis, how they, what approximations they make to make them simpler. And I'll list them, and I'll also tell you kind of what is a dangerous assumption. And you'll see pretty quickly that sometimes it does materialize. So usually the approximations that we make in these types of conditions are that signal through the amplifier is much stronger than feed-forward signal through the feedback network. Okay? In other words, what we're saying is that the magnitude of the Y21A is much bigger than Y21F. Those are the coefficients associated with amplifier and feedback current sources, right? Or voltage-controlled current sources. You look at previous expressions, that just means that this component here can be neglected with respect to this Y21A over here. Right. So that from there, my A is usually going to be just minus Y21A over YI, Y0. Right. So I don't have to worry about Y21F. The second one, and you know, this approximation sometimes doesn't hold. In fact, we'll do pretty quickly toward the end of the class an example where this doesn't hold. And depending on the values of the resistors and the loading network, this may be a huge error or could be a very small error. The other one is that the feedback signal through the amplifier is much smaller than feedback signal through the network. Through feedback network. This is what we're designing the feedback network for, so that it can more easily pass the output signal to the input rather than going through the amplifier itself, right? So, and this assumption is very often true. So Y21A, that was the reverse direction to the amplifier, is much smaller than Y12F. So again, what this means is that our F is really going to be just Y12F. Right. If you remember the previous expression, our F was the sum of these two. Well, this one we can neglect. Oh, sorry. This one we can neglect, and this one not. Okay. So when we're done with this, the way this maps itself to the topology is that we're going to have something that looks like this. IS. We can take all these impedances and put them in, or admittances and put them in parallel on the amplifier side. And then we're going to have 121A times VI. VI is here. And then what we have here is Y22A. And then we have Y22F. And also Y load. This was V out. And then you look what's here, it's really just an open port. Because we don't have Y12A, Y21F. Right, should be here, but it's now gone. And then on the other side, what's left really is Y12F times V out. and that attaches here. So now I can say, okay, this is my feedback. Or I can say new feedback network. And then I can say that this is now my new amplifier, new basic amplifier. Notice that YS plus Y11F plus Y11A, all these we label them as YI, or the input admittance, and then all of these at the output in parallel, they were YO. Right? So we really have a new amplifier that has YI as input admittance, and it has YO as output admittance, and a current-controlled, voltage-controlled current source. Right? So that's a generic amplifier model. And then we have an ideal feedback. So this picture over here really kind of spot on maps onto our ideal feedback type. Right? When we did the shunt model, we said you don't load the output. So you just measure the voltage, and then you just supply the feedback current to the input of the amplifier. And this is exactly what it is. We've now absorbed the loading effects into the amplifier input and output impedances. Right? Okay. So now you can go and kind of do the analysis on this to try to figure out the parameters. And sort of in practice, if you look at, you will isolate the feedback network, and then just go and say, okay, well, this is my feedback network. So I'll figure out the Y11F by shorting the output and looking at the admittance of the feedback network. And then, again, I can extract the Y22 of F by shorting the input and looking at the impedance or the admittance from the output port. And then I can also find so if I look at the current, so if I apply the voltage V out here, then this current over here will be Y12 feedback times VO. So I can find my F as Y12. In this case, I'm kind of not doing the Y21F because I'm assuming that's a negligible amount. But we'll see in some examples, you can have that as a fourth kind of component here where you're going to apply VI here, short this output, and then look at Y21F times VI. Right? So that would be your reverse path, the current. These things we'll do often by inspection. I think if you do enough of these problems, you'll be able to kind of just see the network and kind of figure out what are the parameters that you're going to use. Okay, so let's do an example just so people get a little bit comfortable with this. So let's say we have an amplifier. With RF in feedback. And then we're just going to load it also with RL. If this was an ideal op-amp, RL wouldn't matter, right? Because you would just RF itself would define what the output voltage is, but in this case, it's not an ideal amplifier. And so we can write its small signal model, IS. We're going to have some ZI, which is the input impedance. And then we're going to have some voltage gain times V error. Because we're taking the input is at minus, V error is defined this way. And then we have some ZO, which is the output resistance. And then the feedback goes here, and then we have RL. And then V out. And we're going to say that if we identify the feedback network, it will be this piece, this RF. So this will be our feedback network. Okay, so before we do any transformations of the amplifier, I mean, this is obviously a shunt-shunt kind of example, right? We have the current summation right here from the feedback, and then we're sensing the voltage here from the output. So this is shunt-shunt. But let's first take a look at how this RF resistor maps to the Y parameters of the two-port network. And if you wanted to see the, how complicated a two-port becomes for a simple resistor like this, right? Let's say this is grounded, right? Okay, so we want to represent this as something like this. Y11 feedback, and then we have Y12 feedback times V2. Y21 feedback times V1. And then Y22 feedback. And we're applying a voltage V2, current I2 flows here. Okay, so we're going to do the same exact thing that we did at the beginning of the lecture when we defined the Y parameters. We're going to start nulling the input-output voltages and measuring currents, and we're going to figure out each one of these elements, right, what it is. So if you look at Y11 feedback, that was I1 over V1 when V2 equals 0. Okay, so in this case, that's 1 over RF. Then, if we look at Y22F, this will be, again, I2 over V2 when V1 equals 0. So that's, again, 1 over RF. And now if we look at Y12, that's I1 over V2 when V1 equals 0. Well, that's minus 1 over RF, because the current flows in the opposite direction of the voltage applied, right? Okay, you can still see it. And then you have Y21F, which is I2 over V1 when V2 equals 0. And that's, again, minus 1 over RF. So that's the complete network model, like mapping a simple, series resistor into the Y11 parameters. However, this now gives us a notion of how this resistor actually loads both the output of the amplifier and the input of the amplifier. And we can go and from here really clearly figure out what A is and what F is. So that's the whole point of this exercise. If we now go and rewrite the model, we can say that, OK, well, IS is here. And then what we have is we can move the RF, which is from the feedback section, and then ZI, and both of these are in parallel. And then on the other side, we have, I'll just turn the voltage-controlled voltage source into voltage-controlled current source with the Norton-Thevenin equivalent. So we're going to do AV times V error over Z naught. And then I'll have Z naught over here. And then I'm adding RF, which was really 1 over Y22F. So I'm just adding it up here. The same thing we did in the idealized, in the sort of most general case. And then there is RL here. And then we have V out here. And then I'm feeding back just V out. So there's nothing left in this part of the network. And then on this side, I have Y12F times V out. That loads over here. So notice that what I did wasn't quite the same as what was derived here. I neglected one parameter. Okay? So if you look at these expressions and you look at what I've done here, who can see which parameter I neglected? So this Y12 will be minus 1 over RF. Right? This thing here would be Y11 feedback. This will be Y11 amplifier. This piece over here, or I can say this is VI, and VI is here. So this piece is Y21 amplifier. This is Y22 amplifier. This is Y22 feedback. This is Y load. So which feedback parameter did I neglect? Y22 is here. Yeah. I neglected this controlled source, right? Which is Y21F times VI. This one is also minus 1 over RF, right? So it's not clear I should have neglected it, right? But just for the approximation, I do, right? And this is often kind of what's really the core difference between how we do things with return ratio analysis and what happens when you do two-port. It just becomes too cumbersome to include that from the get-go and then just do all the expressions. So I'll neglect it for now, and then we're going to do another example where we have it. But so from here, again, this is my basic amplifier. or my new amplifier, and then this is my new network. As you see, this is an ideal representation, right? It's the same as the shunt that we originally looked at, and I can also just go ahead and really de-embed A and F from this piece, right? So this is the feedback current, and I can say that for A, I'm looking for A that forms closed loop as A over 1 plus AF, right? So A will be, for I feedback equals 0, what's the forward gain? And so that will be AV times VI over Z0, that's my source. And that equals to V0 over Z out in parallel with RF in parallel with RL. And then VI will be IS of RF in parallel with ZI. And then we can write A as V0 over IS when I feedback equals 0. And that equals to minus AV times Z0 in parallel with RF in parallel with RL, RF in parallel with ZI over Z out, and then can simplify because this piece over here is Z out times RF in parallel with RL over Z out plus RF in parallel with RL, and this and that will cancel out. So what is F from here? F has to represent the flow of information from the output to the input. So any brave souls? Which current source, voltage-controlled current source, represents the flow of information from output to the input? Yeah, Y12 in general, and whether it's through the amplifier or through the feedback, right? We don't have one for the amplifier, right? Because it wasn't in the model, we assumed it's gone. And so the only one that remains is Y12F. So our feedback is minus 1 over RF. And indeed, if this was an ideal op-amp, 1 over F would be, or minus 1 over F would be your gain, right? And so you'd essentially get that your gain is just RF. You're rushing current through the feedback that is RF. You're going to get a voltage that is that input current times RF, right? So that makes sense, sort of as a sanity check. Now we have F and we have our A. We can then go and not only compose the closed loop from this formula, but because our impedance, our feedback model is now kind of the ideal feedback model, because feedback network is not loading the amplifier anymore, we can also infer or use the formulas that we derived for the impedances, right? So for the impedances, oops, okay, that's not good. We want to, okay, keep the annotations. We don't want that. Okay, I wanted to add one more. This is really annoying. This is why Windows XP was discontinued. Okay. Okay, great. So we can do, just add one more slide. Okay, so what we can do is look at the impedances. Okay, so we can look at the impedances, and if you look at here, the input impedance of the amplifier itself. Now, if we look at this whole block as the new amplifier, the input impedance into the amplifier is now RF in parallel with ZI. Right. So if we have a shunt input, and we know that T equals A times F, then what is the new ZI? Okay, so one, it's possible to be here or here. So the question is, where is it? If it's shunt, yeah. Yeah, so you want this thing to admit as much current as possible, right? So you're dividing down the impedance, right? Okay, and then if we look at the output, let's see what the output impedance is. Anybody wants to say? Yeah.
Same formula as Ian.
So ZOA divided by 1 plus T.
Yes.
Okay, but what's ZOA? What's the native, now the amplifier output impedance? If you look at this whole thing as the sort of the upper thing as the new amplifier block, what's the output impedance of that amplifier? Yep, it's all these three guys, right? So that's ZO in parallel with RF in parallel with RL. So here is the contribution of feedback, right? Both in the input and the output impedance. And then, yes, we can say because, so because of shunt, we get to divide the input impedance. And then because shunt at the output, we also get to divide the output impedance by the feedback loop gain. Okay. I don't want to start the new example. We're going to do that in the next class. But I'd encourage you to sort of go back, and let me just show you maybe just for 1 minute, kind of show you something with which you can kind of go back and compare to the return ratio derivations that we did. For the return ratio examples, we used something like VI R1 minus plus R2. And then we load this. I hope people see this is exactly the same topology as we just analyzed, right? I don't know if people see. No. Okay, let me explain. Can anybody explain how this topology is the same as this topology?
you do the equivalent of VI to the current source resistor?
Okay, so you're saying Thevenin to Norton type thing. So okay, we can take this piece and make it a current source of VI over R1, and then have R1. And then that gets into the amplifier. Okay. And then what do I do with this R1? Well, no, this node actually, this is not an ideal op-amp, right? So we're going to have inside, we have some R in, right? That's right. So we're going to say that in our ZI, right? So the ZI here will be R1 in parallel with RI, right? And in this case, we just had ZI. But all the math now works out, right? It's exactly the same. It's just that I lump this R1 in parallel with the input impedance. So if you go back to return ratio formulas, you can essentially go and crank them out to see what you get, and sort of where the differences are. And then we're going to do the next one more example on shunt on a simpler circuit at the beginning of the next lecture and move into the new topologies. Okay? So hopefully you didn't get too scared of two-port.